now know everything that we need to know in order to solve any old log equation, as long as all of the logs have the same base. Let's just see one more example of going through that whole process. So our first step is to just spot all of the log terms in our equation. We have here one term with a log, and another, and another. And then we have a number here, and a number here. Our first move is going to be to collect all of the log terms on one side, and all of the constants on the other. So we're going to start by adding log base 3 of x plus 8 to both sides. So the left-hand side will have the log base 3 of 2x plus 17 minus 2 times the log base 3 of x plus 6 plus the log base 3 of x plus 8. And then we'll still have a plus 5, and the right-hand side, that equals 6. Next, we'll subtract 5 from both sides. And so we have the log of 2x plus 17 minus 2 times the log of x plus 6 plus the log of x plus 8 equals 1. In reality, we could have done those two steps in either order, or we could have combined them into one step. Now that we have all the log terms collected, we need to combine all of our logs. Now, this 2 here might give us a moment's pause. We might think, should we isolate that log? Is there any way we can get rid of that 2? Well, unfortunately, because 2 is not a common factor, throughout that entire left-hand side, there's nothing we can do to get rid of it. So when we're using our log rules to combine, we'll have to use our log rules to push that 2 into the log. So now we're on using log rules to combine. First, we're going to use the power of a power rule to push that 2 into the argument. If we had other coefficients, we would push them in at the same time. So, first term we leave alone. That second term, the coefficient 2 outside becomes an exponent 2 inside. Third term we leave alone, and nothing happens on the right-hand side at this point. Okay, and now we have both addition and subtraction. When we combine, we're going to get a fraction of some kind because there is subtraction in there. Positive terms go in the numerator, negative terms go in the denominator, and then we have another positive term that goes in the numerator. And we didn't do anything to the right-hand side at that stage, and we'll remember to write the base on our log. Okay, so now we have a single log equals a number. Next, we rewrite an exponential form. So now the left-hand side will be just this rational expression, and on the right-hand side, we have our base of 3, and the 1 becomes an exponent. And of course, 3 to the 1, that's just 3. Okay, we are done with the new stuff, right? We're done dealing with the logs. Next, well, next we need to solve this rational equation. We can end up with any of the kinds of equations that we've seen before after we get rid of our logs. Whatever kind of equation we get, we need to solve it. So first we need to get rid of that denominator. So I'm going to multiply both sides by x plus 6 squared. On the left, That'll cancel out the denominator. So we'll have 2x plus 17 times x plus 8 equals 3 times x plus 6 all squared. Okay, we no longer have a rational equation. We now have a polynomial equation, which we now have to put into standard form. So in order to do that, we need to multiply out on both sides and then get all of the terms onto the same side. So on the left, we'll have 2x squared plus 16x plus 17x plus 17 times 8. That's a job for a calculator. That's 136. On the right, I'm going to deal with the exponent before the multiplication because that's what order of operations says. I'll have 3 times x squared plus 12x plus 36. So now I'm going to go through, I'm going to combine like terms on the left. 2x squared plus 33x plus 136 equals 3x squared plus 36x plus 3 times 36 is another job for a calculator. That's 108. Okay, because I like my x squared term to be positive, I'm going to subtract everything from the left-hand side. And so we'll have 0 equals x squared plus 3x minus 28. Oh, that's not too bad. Okay, let's see if we can solve this by factoring. We have a quadratic with leading coefficient 1, so we can use the shortcut. We need two numbers whose product is negative 28 and whose sum is positive 3. Well, I think that's going to be positive 7 and negative 4. So we get the solutions x equals negative 7 or x equals 4. Okay, so now we have our two potential solutions. We need to check whether those really work or not. And there are two ways we could do that. Method 1 would be to plug in to the original equation. Looking at my original equation, it looks really long and complicated, and I would really prefer not to trudge through plugging into that. I don't want to do it by hand, and I don't particularly want to do it on the calculator because of those log base 3's in there. So we could do it that way, but I'm going to use the other method, and that is to just check the domain of all the logs. So one of the arguments our logs have is 2x plus 17. We need 2x plus 17 to be greater than 0, so 2x is greater than negative 17. X is greater than negative 17 halves, which is negative 8.5. Our second log, we have argument x plus 6. So we need x is greater than negative 6. And our third argument, we have x plus 8. So we need x is greater than negative 8. X is greater than all of these if it's greater than negative 6, right? They're all greater than inequalities, and negative 6 is the biggest one of those. X needs to be greater than negative 6, which means x equals 4 is in, and x equals negative 7 is out. And we can plug that in to check that x equals 4 truly is a solution. We'll have the log base 3 of 2 times 4 plus 17 minus 2 times the log base 3 of 4 plus 6 plus 5. That's the log base 3 of 25 minus 2 times the log base 3 of 10 plus 5, which is going to be some horrible decimal. We'll put that into our calculator in a moment. On the right, we have 6 minus the log base 3 of 4 plus 8. That's 6 minus the log base 3 of 12. Let's see what we get here. Our left-hand side, we have the log base 3 of 25. That's log of 25 over log of 3 minus 2 times the log base 3 of 10. That's log of 10 over the log of 3 plus 5. And that's that awful decimal 3 and a bit. Right-hand side, we have 6 minus the log base 3 of 12 is log of 12 over log of 3. And we get exactly the same awful decimal. Even though those don't work out to nice numbers, we do get the same number on both sides. Those really are equal.